Good morning. It is an honor to have you here. The examining panel, my supervisors, colleagues, friends, the audience, thank you very much for coming. As Professor was introducing me, it just struck me that when my father gave me the name Ndibazza, he didn't know that it really meant I'll bring you back. I'd like to say a special thank you to my friends, colleagues, and the staff who came here early in the year in preparation for this. This time, though, I've brought you back, and I hope that we will see the occasion to conclusion. The title for my research is quite a mouthful, but simply put, my topic is childhood malaria. The majority of us here will have had at least one episode of malaria in our lifetime. But did you know that helminth infections might have something to do with us having malaria? Please join me to explore this possibility as we go through the presentation. This is the overview of our discussion this morning. I'll try not to keep it lengthy. First, I'll give you some background on the topic to be discussed. This will lead us into the purpose of the justification of the study, purpose and justification, followed by a brief literature review. And that too will lead us into the hypothesis and objectives. Then I'll share with you the methodology I used for the research, after which we shall go through the major findings. After that, we shall explore the limitations and strengths of the study, and then a summary of the results and discussion. Lastly, a couple of recommendations arising from this research. And then, of course, acknowledge the team that supported me through this experience. Starting with a brief background on malaria and helminths. Malaria remains a major infectious disease of public health concern globally, but more so in the tropics. The 2014 World Health Organization report stated that more than 200 million cases and more than 500,000 deaths are recorded annually. Moreover, 90% of the malaria deaths occur in sub-Saharan Africa. And we still know that pregnant women and children under 5 years are the ones who bear the greatest burden of this illness in our populations. That is an image very typical in our hospitals, with mothers taking care of their very sick children, oftentimes receiving a blood transfusion that may follow severe anemia that's usually a complication of malaria. Despite several malaria control interventions for a long time now, and a reduction in the incidence of malaria of about 30% globally, the World Health Organization reports that Uganda remains one of the highest malaria-burdened countries in the African region. So we are doing pretty good, bad. I think we need to improve. Then again, helminths. As I suggested at the beginning, helminths might have something to do with malaria. Helminths are another major public health concern, especially in our region. Over a third of the human population is said to be infected with worms. And when we talk about worms, often we are thinking hookworm, ascaris, trichuris. But with our water bodies in Uganda, we also have schistosomes. And yes, mothers do dip their babies in the water for a bath or for playtime, and the babies may get infected with schistosomiasis. So the purpose of the study was to explore the associations between early childhood malaria and both maternal and child helminth infections. Justification for this study was, as I've mentioned, that malaria and worms still cause major public health concern in our communities. They are major causes of morbidity in mothers and children. Secondly, that the effects of exposure to helminth infections in pregnancy have not yet been explored thoroughly, and there may be some to look at for childhood malaria. Yet, mass drug administration programs have already preceded thorough research on the effects of deworming in pregnancy and early childhood on childhood illnesses such as malaria. So using this conceptual framework, a working hypothesis was established to look at maternal helminths and maternal malaria infections in pregnancy. In addition, to look at child helminth infections in early childhood and their effect on childhood malaria. And in addition, to explore the effect of anthelminthics on mother and child helminth infections and consequently on childhood malaria. To come up with the hypothesis, I explored the existing scientific literature on malaria and helminth associations. 5 key areas were looked at. The first one was looking at helminths and Plasmodium distribution in our geographical distribution in our area. Studies have shown that helminths and malaria are really co-endemic in our areas, in the tropics, and co-infections are more often common than rare in our populations. The second key area was to look at studies that have tried to explore the association between malaria and helminth infections. And although about more than 10 studies have been carried out in this area, the results are conflicting. Some studies suggest that that worms are bad for malaria, while other studies have suggested a beneficial effect of worm infections for malaria. And yet still, other studies have shown no association between malaria and helminths. So for the third area, I looked specifically at the association between maternal malaria and helminth infections in pregnancy. The 3 studies, including one here done in Entebbe, suggest that mothers with helminth infections were more likely to also have pregnancy malaria. So there was a positive association there. The 4th area looked at the role of helminth infections on immune responses. Because if you have a clinical association between helminths and malaria, the question was, is there a possibility this is being driven by some immunological factors in the background? And yes, studies have shown that chronic helminth infections induce a Th2 immune response that may result in a down modulation to the helminth infections themselves, but also to other antigens. And the 5th area looked at the question, how would exposure to helminths in pregnancy affect the child? Any immune modulations in utero, could this be revealed in clinical outcomes? So the scientific literature brought together seemed to suggest that exposure to malaria and worms in pregnancy may influence the immune response of the fetus and later on even the child, resulting in a failure to mount a good response in the case for malaria infection, resulting in increased childhood clinical malaria, or on the other hand, resulting in the development of resistance to malaria infection. So now going to the hypothesis and objectives. I'd like to note that this was an epidemiological study based on an immunological hypothesis. As the professor has said, I have practiced as an epidemiologist. I do not claim to be an immunologist. The hypothesis, working hypothesis, was then designed to say childhood malaria is modified by prenatal exposure to Plasmodium and helminth infections, and by anthelminthic treatment in pregnancy and early childhood. So now I'd like to take you through the methodology I used for this research. My PhD research was nested in a large birth cohort, the ENTEBBE Mother and Baby Study. The principal investigator for this study was Professor Elliott, and the study was carried out in the ENTEBBE municipality and the neighboring Katabi sub-counties. In this study, 2,507 pregnant women were enrolled, accruing 2,345 live births between April 2003 and November 2005. The hypothesis for the mother study was that helminth infections can influence the immune response to antigens other than the helminth antigens themselves, call them bystander antigens, that these effects can be established during pregnancy, and that these effects might be modified by anthelminthic treatment. Key areas for inclusion criteria were that the mothers were resident in the study area, they were preparing to deliver at the ENTEBBE General Hospital, and willing to participate in the study. The exclusion criteria key areas were that the mother didn't have a severe anemia, and that they didn't have apparent symptoms suggestive of liver disease, which might be related to chronic or severe helminth infection. In addition, mothers were only enrolled for one pregnancy in this trial. For the ethical considerations and approval, the main ethical concern addressed at the beginning of the study was the question of whether it was okay to use a placebo in an anthelminthic trial in pregnancy. But before 2002, even when the WHO had recommended the use of anthelminthics in populations with high infections, there hadn't been any clinical trials to investigate effects of deworming in pregnancy on childhood outcomes and in pregnancy. In addition, so that justified the carrying out of the trial at that time. In addition, as in many other studies, informed consent was obtained during pregnancy, mothers having received literature from the study staff about the study procedures. For the children, when they reached age 1 year, parents or guardians consented for the childhood trial component. And ethical approval was obtained from those three institutions. The sample size estimation and randomization were again based on the mother cohort. Specifically, for malaria, the incidence rate for malaria in infancy was assumed to be 0.5 per person year and 0.8 in the older child in the maternal placebo group. The interventions in pregnancy, albendazole and praziquantel, were considered to have independent effects. Other considerations were also included in the sample size estimation, like a 10% loss per year before delivery, 25% in infancy, and a 10% later. And again, specifically for malaria, about 2,500 participants would be able to show an 18% reduction or a 19% increase in childhood malaria. At this stage, it wasn't clear which were the effect of deworming would be. The random allocation sequence for this trial was generated by a statistician at the London School of Hygiene and Tropical Medicine. Data collected and infections diagnosed. The mothers provided blood and stool samples during pregnancy, before enrollment. And after they had had the child, they also provided a stool and a blood sample. On the other hand, the children provided blood and stool samples when they attended the study visits at the research clinic and when they had an illness event. So Leishman-stained thick blood films were done for malaria parasites. Modified Notes method was used for the Manzanella perstans infections. The cattle-car slides were used for hookworm and other helminth eggs. For the antibody responses, standard ELISAs were carried out to the malaria antigens epical membrane antigen 1 and merozoite surface protein 1. In addition, HIV serology tests were carried out. All clinical data and other data, study-related data, was entered on pre-coded questionnaires into access databases and analyzed using Stata. We also were able to locate the participants' residences and georeference the participants' residences using the global positioning system receivers. And later, when the data was compiled in 2 data sets, using the SearchScan software and the ArcMap software, we were able to generate maps showing the prevalence of infections in the study population. But I was also able to use this data for adjusting for confounders in the observational analysis, as you will see. So you may ask, what exactly was the candidate's role in the big cohort? Quickly, I'll take you through this. During the study in 2002, my main duty was to prepare the child research clinic, the children's research clinic, where they would be followed up for study visits and childhood illnesses. But before the children arrived, because we were enrolling pregnant mothers in the ENTEBBE General Hospital, I was also involved in ensuring that the data collected for enrollment and screening was clean and then sent to the statistics department. When our babies arrived at the clinic, I had a team of about 4 other doctors, 4 nurses, and support staff. And here we provided general pediatric health care, including immunizations, and taking care of any morbidity, childhood health morbidity, and in addition, collecting data, study data specific to the objectives of the study. So we had a full-fledged pediatric clinic, 8 to 5, Monday to Friday. And any children who were sick over the weekend were referred to ENTEBBE General Hospital. In addition to that, I also laid and designed a program that trained about 100 community workers who visited the children at their homes. This group of workers helped us a lot because they reminded the parents to bring in the children for the study visits. But they were also able to take temperatures, body temperatures, and if a child had a fever, they asked the mother to bring the child to the study clinic. So now I'll take you to the analysis and major findings. The key maternal characteristics for the pregnant women in this study, to give you an idea of what the population looked like. The mother's mean age was 24 years. The majority of them were Baganda, as would be expected in the study area. Half of them had none or only a primary education, while 84% of them reported that they were married. Again, the majority of them were of a low economic status, hardly earning more than £10 a month. Roughly half and half were enrolled in the 2nd and 3rd trimester. Mothers were not enrolled in the 1st trimester. At enrollment, 68% of the pregnant women had at least one worm infection, which was very high at that time. The commonest infection was hookworm infection. 21% had Mansionella perstans, 18% had Schistosoma mansoni, and 11% had asymptomatic malaria. We looked at asymptomatic malaria from peripheral blood samples. 8% then had a co-infection with malaria and any of the other worms. And in addition, 11% had HIV. Just to remind you, the primary outcome was child clinical malaria. Then in addition, secondary outcomes were asymptomatic malaria and antimalarial immune responses in the child. Clinical malaria was defined as a recent fever or an auxiliary temperature of 37.5 degrees centigrade or higher, plus any level of parasitemia, while asymptomatic malaria was defined as the presence of Plasmodium falciparum in the absence of a fever on the day the child came for their annual study visit. In all, more than 33,000 clinic visits were accumulated across the maternal infection groups. The overall incidence rate of childhood malaria was 34 per 100 person years, highest in the first and second years of life, as is normally the pattern, and tailing off after the third year. The mean prevalence of asymptomatic malaria in the children was 5.4%, again highest at age 2 years. The first specific objective was to look at the association between maternal helminth and malaria infections on childhood malaria. And the results of this analysis were published in that paper. So this shows the flow chart, the progress of the mothers right from screening and enrollment, ending up with 2,507 enrolled, and from this group of mothers, 2,356 with delivery data. We were lucky to have 32 twin pairs and 1 triplet set. However, these were excluded for the observational analysis, ending up with 2,289 mother-child pairs. For the observational analysis, crude hazard ratios, we obtained crude hazard ratios using Cox regression with robust standard errors to correct for within-child clustering. The confounding factors that were adjusted for included maternal age, education, parity, socioeconomic status, whether the mother had a net, we didn't ask for whether they used the net, their geographical address, as well as HIV status. To compare childhood parasitemia by the maternal infection groups, I used random effects logistic regression. And then again, maternal malaria and HIV infections, plus child albendazole, were assessed as possible effect modifiers for this analysis. So this is the first set of results for the observation analysis between maternal infections and child malaria. The Kaplan-Meier graphs show cumulative incidence of childhood malaria from age around just before 6 months to age 5. And again, by maternal malaria infection, maternal Marsanella infection, maternal hookworm infection, and maternal Marsanella infection. On the y-axis, we have the proportion that failed. And as you can see, for all maternal infections, there is a higher incidence of clinical malaria for children born to mothers with malaria, Marsanella, hookworm, and slightly so for Schistosoma marsoni. The adjusted hazard ratios corresponding for these were 1.23 for malaria and 1.23 for hookworm, slightly lower for Marsanella. These three were statistically significant, and we do not have a statistically significant effect for Marsanella on child clinical malaria. A similar analysis was carried out to explore the association between maternal infections and asymptomatic parasitemia in childhood. The first column has the maternal infections. The second column has the percentage of children who were ever parasitemic at their annual visits. Then a crude odds ratio was calculated, as well as an adjusted odds ratio, including the confounders listed below. For hookworm, for children born to mothers with hookworm, we had about 6.6% in that group that were ever parasitemic, compared to only 4.2% in the group of children who were born to mothers who did not have hookworm, giving us an adjusted odds ratio of 1.57 that was significant. Infection with Marsanella persistens shows a similar pattern, higher proportions in children born to mothers with Marsanella compared to children born to mothers without Masonella. However, the association was only of borderline significance. And then for Schistosoma masoni, once again, as with clinical malaria, no significant effect. Maternal helminths and malaria infections were not associated with child antimalarial immune responses. I have not shown the data there. However, because of the consistent association between maternal hookworm and child clinical malaria, and with the hypothesis that this might be due to immune modulation, I looked at the association between child antimalarial responses to a falciparum infection stratified by whether the mother had had hookworm infection or not. And the box plots here are for the responses to AMA1 and MSP1 at age 1 year and at age 5 years. And as you can see with the upper row, children born to mothers who had hookworm had a lower mean anti-AMA1 response compared to children born to mothers who did not have hookworm at age 1. And the interaction was significant. We see a similar pattern at age 5, where children born to mothers who had hookworm infection had a lower mean antibody response compared to children born to mothers who did not have hookworm. However, we do not see a consistent pattern with responses to MSP1. So in summary, maternal malaria, hookworm, and M. persistens infections were associated with increased clinical malaria in the offspring. And maternal hookworm was associated with a lower mean anti-AMA1 immune response to a falciparum infection among children aged 1 and 5. This takes us to the second objective. The second objective was to look at child helminth infections, the infections they acquired from age 0 to 5, on child malaria. Our children showed the expected helminth infections in this age group. The highest prevalence was for trichuris, followed by ascaris. A few had Schistosoma masoni, and some hookworm. But we also saw that the prevalence of infections cumulatively increased with increasing age. From the geographical data collected for the participants' addresses, I was able to map the distribution of the helminth prevalence in the study area. This area is the one towards the airport in Entebbe, and it had the highest prevalence of helminth infections. The area in the middle is along the highway to Kampala, and the area with the second highest helminth prevalence is towards Nkumba. For the children, I carried out similar analysis between child helminth infections at age 4 years and clinical malaria in the 4th year. The helminth infections I restricted to age 4 years with the assumption that by this time the children had had several infections, even though they were receiving, half of them were receiving albendazole, the possibility was that repeated helminth infections or chronic infections will affect childhood malaria. I have a table to show the results. The first column is the child infections with trichuris, ascaris, hookworm, and masoni. The second column shows the incidence rates per 100 person years. I have the Cox hazard ratio and the adjusted hazard ratio with the p-value. Again, confounders were adjusted for mostly maternal hookworm, maternal factors, maternal hookworm, age, education parity, socioeconomic status, water source, the geographical zone, and, in addition, child albendazole. So for children who had trichuris infection at age 4, we see that the incidence rate at 34.5 is higher than among the children who did not have trichuris at age 4. And the adjusted hazard ratio was significant. A similar pattern is seen for ascaris infections among the children compared to those who didn't have ascaris. A similar pattern for hookworm infections compared to those who didn't have hookworm. And a slight difference for schistosoma marsoni. However, we had very few children with schistosoma marsoni infection. Again, I looked at the association between child helminth infections and asymptomatic parasitemia, restricting this analysis to age 5 years. Similar to the table before, but this time looking at the odds ratios. We had 8.9% of children with trichuris were parasitemic at any one time, compared to only 4.6%. A similar pattern for ascaris, with a larger proportion with ascaris being parasitemic at any one time point, and a lower for those without ascaris, and for hookworm. I then looked at the association between child helminth infections and antimalarial responses. Overall, there wasn't any consistent association between the children's own helminth infections and antimalarial responses. However, for infections with S. marsoni, the geometric mean was higher for children infected with S. marsoni compared to those without, with a significant regression coefficient. So in summary, infection with trichuris, ascaris, and hookworm was associated with increased clinical and asymptomatic malaria without any consistent associations between child helminths and antimalarial responses. The third objective was then to look at the anthelminthics in pregnancy, albendazole and praziquantel, on childhood malaria. The results for this analysis are published in that paper. For the maternal trial, 2,515 pregnant women had been enrolled at the start. 8 were excluded because eventually they were found that they were enrolled a second time. So we had, at the end, 4 groups. Mothers received either albendazole plus praziquantel, received albendazole alone with a placebo for praziquantel, praziquantel with a placebo for albendazole, or 2 placebos. For the statistical analysis, the trial component was by intention to treat, and the effect of the anthelminthics was on effect of a single dose. It was assumed that the effects would be independent of each other, so no interaction was assessed. Subgroup analysis to examine the effect of albendazole among the children of mothers with hookworm and the effect of praziquantel among the children of schistosoma marsoni was also carried out, assuming that the effects there, if they were, would be larger in this population. Several methods were used to obtain the results for the trial analysis. I'd like to note that random effects logistic regression models were used to compare repeated childhood parasitemia because the children came in every time they attained their birthday. So some children would have several parasitemia results, while others would have had 1 or so. So the next slide is going to show you the association between maternal anthelminthic treatment on child clinical malaria. To note, the randomization resulted in a similar distribution of the baseline characteristics between the 4 treatment groups. From the Kaplan-Meier graph, similar to the one I've shown before, the blue line is the group for the mothers who received albendazole, while the red is the group for the mothers who received placebo. And this is similar, looking at praziquantel versus the placebo. So there was no effect of albendazole nor of praziquantel on childhood clinical malaria. The analysis, looking specifically at the group of mothers who had hookworm and the group of mothers who had Schistosoma mansoni, maternal helminth treatment on child malaria stratified by the mother's infections, also showed no effects in these subgroups. And lastly, for maternal helminthic treatment, I did an analysis on child antimalarial responses, and again, anthelminthics had no effect on child antimalarial immune responses, where we see the regression coefficients all including 0. At year 1 and at year 5 for both responses to AMA1 and MSP1. So in summary, deworming in pregnancy had neither a beneficial or adverse effect on malaria. Deworming in pregnancy also had no effect on child antimalarial responses. This takes us to the last objective. Looking at anthelminthics in childhood, albendazole's effect on childhood malaria. The children were started in the childhood trial at age 15 months until they were age 5. Of the 2,345 live births, 2,016 were enrolled into the childhood trial. And we had 1,010 in the albendazole group. Placebo had 1,006. All the children were followed up to age 5 years with those numbers in the different groups. Children before age 2 received albendazole as a syrup, 200 milligrams, and children from 2 and above received albendazole as a tablet, 400 milligrams. Similar analyses were carried out for the childhood trial. Only for the children, the time at risk was from age 15 months, or the first time they came in after age 15 months, until they were lost to follow up, or passed away, or attained age 5. To note also, child albendazole was assessed independently of the mother's anthelminthic treatment. And interactions between child albendazole and the mother's infections was also explored. So again here I'm showing a Kaplan-Meier graph. The red is the placebo group and the green is the albendazole group. As said, this is about 15 months age to age 5 years and showing the proportion that failed. We see that the children who received albendazole had a lower incidence rate of clinical malaria compared to the children who received placebo. The hazard ratio was 0.85, was statistically significant, whereas for the asymptomatic malaria, although there is a suggestion for a beneficial effect, it did not achieve statistical significance. A subgroup analysis was also carried out to find out whether the effect of albendazole on childhood malaria differed by age groups. And the results suggest that the beneficial effect was strongest in the second year of life. So on this graph we have 2, 3, 4, and 5 years, the hazard ratios for the different age groups. And this is the hazard ratio for age 2 compared to that for 3 years, 4 years, and 5 years, with wider intervals and including 1. Compared to the 0.85 for the general cohort, we had a hazard ratio of 0.66 for the group age 2 years. A similar graph looking at the effect of albendazole on asymptomatic malaria by age. Again, at age 2 years, an odds ratio of 0.51 compared to the different odds ratios for 3, 4, and 5 years. Having collected data on childhood helminths, I did another subgroup analysis to find out whether the effect of albendazole that seemed to be greatest in the second year was modified by the childhood helminth infections in the second year. This table shows the association between albendazole and clinical malaria in the second year of life by the child helminths. Here we have whether they had helminths or none, and what intervention arm they were in. And for the incidence rates per 100 person years, we see that children who had helminth infections had a lower incidence rate compared to those who did not have, suggesting that the effect of albendazole was modified by child helminth infections. A similar pattern is seen when I looked at the effect of albendazole on asymptomatic malaria. However, the numbers are pretty small and might explain why statistical significance is not attained. Looking at child albendazole on child antimalarial responses, the conclusion was that albendazole had no effect on child antimalarial immune responses. So in summary, albendazole in early childhood had a beneficial effect on clinical and asymptomatic malaria. The effect seemed stronger in the second year of life and among children with helminth infections, without any effect on antimalarial responses noted. So now I'd like to share with you the strengths and limitations of this study. The nested study within the ENTEBBE mother and baby study was a privileged study, I must say. It was a randomized placebo-controlled design for one, but a very large birth cohort with a long follow-up time. It's rare to find a cohort that follows the child from in utero to early childhood. In addition to that, an extensive data of potential confounders was also collected for the analysis. And in conclusion, I consider the consistent results for the different related outcomes to suggest possible true associations. For the limitations, the main limitation was a single sample for ascertaining malaria and helminth infections, which could result in misclassification bias. However, this would only dilute the effect sizes observed. The other limitation was possibly the timing of infection assessed. For example, in pregnancy, it was a one-time point assessment for malaria and stool, and yet we could have missed the infections at other time points. For the observational analysis in childhood, the low helminth prevalence among the children was one limitation. At age 5, only 11% were infected. And then again, the generalizability of the results and the observations may be questioned because non-participating children in the study area could have had a higher prevalence of helminths. Remember that half of the children in this analysis were receiving quarterly albendazole during their early childhood. So in summary, from the observational analysis, just a repetition, infection with malaria hookworm and Mastonella in pregnancy increased malaria in early childhood. Hookworm infection in pregnancy compromised the child's antimalarial response to an infection with falciparum malaria. And in addition, infection with Ascaris, trichuris, and hookworm in the preschool-aged increased childhood malaria. For the observational analysis, the question was the association seen between maternal helminths and child malaria. Child helminths and child malaria. Could that be a geographical reason, considering that malaria and hookworm tend to be in the same environment? Also considering that children born to mothers with helminths or malaria are more likely to be exposed to the same parasites. However, adjusting for geographical location in the observational analysis did not change the observations we saw. The second possibility could be a genetic explanation. Studies have suggested that there is a tendency to polyparasitism in certain people. And if a mother has a tendency to acquire malaria parasites or helminth infections, is that tendency passed on to the child and therefore explaining the associations? However, if you take malaria infection in pregnancy as a proxy for a genetic factor, adjusting for malaria in the observational analysis for maternal infections and child malaria did not change the observations. So it takes us back to the immunological hypothesis that the study had started with. Is it possible that helminth and malaria infections may bias the profile of the antimalarial response, down-modulating the child's immune response to malaria, and such that we see more clinical malaria, more asymptomatic malaria in early childhood? However, because the mothers had received anthelminthic treatment in pregnancy, and we had thought, the assumption was that anthelminthic treatment would remove the effect of helminths. We do not see that in this result. It is also possible that a single dose in pregnancy could not reverse whatever immune response changes had already taken place. For the trial analysis, a recap: anthelminthic treatment in pregnancy, no effect on malaria in the offspring; albendazole in childhood, a beneficial effect for malaria, greatest in the second year of life, and possibly for children infected with helminths compared to the uninfected. So for maternal anthelminthics, as I've said, the absence of an effect on child malaria might be a result of insufficient deworming. A single dose in the second and third trimester, if there are any immune responses that may account for the association seen, probably these are well established before the anthelminthic treatment was given. For the child anthelminthic observation, the beneficial effect of albendazole might be a result of the elimination of helminths as seen in the age group, the 2 years. However, because of the low prevalence of the helminth infection in the children, it is also possible that albendazole has a direct effect on malaria in preschool age children. I'd like to suggest a few recommendations from this study. From the observational results: maternal infections increasing childhood malaria, child infections increasing childhood malaria. I believe epidemiological studies, further epidemiological studies, are still necessary, especially looking at areas with different prevalences. In addition, looking at different age populations. I looked at the age population 0 to 5 for the outcome and noticed that even in that age group, child helminths were associated with child malaria, as has been reported for the older child age groups. In addition, studies should concentrate on the specific helminth-malaria co-infections. So you might find that malaria with Schistosoma mansoni might provide a different outcome compared to malaria with hookworm infection. In addition, immunological studies are necessary to tease out the role of cellular and antimalarial and humoral responses in the malaria-helminth interactions observed in this study and in other studies. Especially so now that the malaria vaccine front seems to be picking up speed. It would be interesting to see how the efficacy of my malaria vaccine may be influenced or affected by the presence of worm infections or the absence of worm infections. From the trial results, there is a need, I would say, to review the role of deworming in pregnancy. Deworming in pregnancy did not affect the childhood outcome. It is also important to ascertain the role of deworming in childhood on child malaria, especially as most programs try to integrate the malaria and helminth control interventions. Secondly, well-designed trials, as I said, in regions with different malaria-helminth prevalences will be helpful to further investigate the appropriate timing for deworming in pregnancy, or should deworming be done before pregnancy in the younger female adults. I'd like to acknowledge the teams that have supported me through this PhD. The Malaria Capacity Development Consortium was responsible for the scholarship that helped me carry out a lot of this work. The Entebbe Mother and Baby Study Team was my mother cohort as well. The Entebbe General Hospital, where the mothers were enrolled and the children followed up, especially the very sick ones. And of course, my doctoral committee. Last but not least, the mothers and babies who took out their time to religiously attend this long follow-up to provide us with the data that I was able to use as a PhD student to present this, share this with you. Thank you very much.